It. Oh yes,
Sorry?
it's on now.
Okay. Students, welcome to our last office hours and hangout for the semester. We are doing this to answer any last minute questions you may have. As you know, we have our final exam available for taking it from tomorrow, uh, 9 a.m. onwards, and it will be available until 9 a.m. on Tuesday. So you can take it at any time during this period. It will be about 3 hours and 15 minutes exam. I think mostly it should uh, not take that long, but we are added 15 minutes. So the real duration is about 3 hours, and we added 15 minutes for any glitches you may face, if any, for the Proctor track. I hope all of you have logged in into your respective Proctor track accounts. You should have received an email and set up the account uh, and tested your machines and so on. If you haven't or have faced any problems about your account, please directly contact David Joyner. I think Chow had posted his email address on the Piazza or announcements. And please make sure that your account is set up properly and everything is okay. Those who are taking it first time, that's probably the those are the ones who might have to set up the new accounts and all that. But others who have already done it before for other classes should be able to just update their software, retest their computers, and be ready with the new setup, if any. So, and those are about the logistics of the exam. And in terms of, we have already uh, gone through a few um, uh, other announcements about the final exam, and hope all of you are ready. The exam will be comprehensive, closed notes, closed book, and so on. Um, just to repeat it, you will be using some scratch paper, blank scratch paper. There are about 8 to 10 multiple choice questions, and there are about 5 to 6 essay type questions, and you will have plenty of time to do it. But the essay type questions need you to work out some things offline and then transfer some of the answers onto the text box that is provided in the Proctor track. Um, if there are any graphs or anything like that, you will be given an exact format in which you have to put it in terms of text, because we do not have support for images in the Proctor track, and so you will be putting maybe as a list of nodes for an edge and so on. You will be given all the detailed instructions, the format that is expected, and that's about the other part of the logistics. The exam is comprehensive, covering all the topics. As you know, we have done this in two parts. The first part was about the processor architectures. What are the peculiarities that are introduced in the processor architecture for facilitating certain characteristics of embedded code, such as energy consumption, code density, and so on, compact code. Um, so many things are introduced in the embedded microarchitectures. We studied that part, including a lot of details about scheduling and VLIW, which are really important for achieving parallelism and performance at low cost in terms of the architectural support for it. And in the second part, we actually saw how to use these through how the compiler generates code And in particular, we have focused on register allocation, how to keep values in registers as much as possible, or how to take advantage of the registered banks and so on, which are present in certain types of microarchitectures, embedded architectures. We dealt with a variety of processors, ranging from DSPs to network processors, and how these processors and their peculiar register organizations or restrictions in terms of code generation allow you to do certain optimizations. So we studied that. So as I have been mentioning, I hope not only you have gone through the slides, but you also read the textbook and the underlying papers. It is expected to know these concepts and algorithms at a high level in terms of what is exactly going on, and there might be pertinent questions about those. So there was a question on PIAS about whether we are supposed to know the algorithms. So the answer is yes. Specific algorithms and concepts, for example, what exactly is maximum weighted path cover and such. So you should be knowing these things, and that's a part of the material. You should have studied and understood the concepts pretty clearly, and should know them to use them, and offline, in other words, with the closed book and closed notes. So that those are the things, and now we will have any. I think we have returned all the homework so far. Um, the only project 2 is being graded. Of course, that's not really relevant for the finals, and it will be graded and returned very soon, in maybe end of this week or early next week. I guess I will leave it to the TS to announce it. Chow and Daryl, do you have any announcements to any of these effects, or any other last minute logistics or other stuff?
Okay, from my point, it's just still about the Proctor track. Actually, I just learned from the John. He says everybody should be in the in the list of account, but when I add you to a test, the Proto track will not email you some notifications. So you needed to log in into the account by yourself to check whether you can see the test. And the username for the account is the gtid at gmail at gt with the gt email. It's not, you cannot using the email address use just configured as alias to your gtid email. And for your first access, maybe you needed to reset the password with your gtid email. So I think that is all part from my point. Just a remind.
What you just, because I don't know how many of them are attending the office hours, would you also mind posting this as an announcement, Chow?
Yes, I have posted in the announcement last week.
Okay, so you have to use the GTID at Georgia Tech as the email, right?
Yeah.
To log in.
Yeah.
And so please follow that and make sure you are able to get into your account. You may not see the test currently today, because we haven't released it or published it yet. But please do make sure that you're able to get in, and once the test is available from tomorrow onwards, you should be able to see it. Any other announcements, Chow or Daryl?
So that is all my announcement.
Daryl, about Project 2, do you have anything to say in terms of when you might be able to return it and so on? Or...
Yeah, I'm planning on grading those Project 2s this weekend, so I'll hopefully have them back Monday or Tuesday of next week, I think.
Okay, great.
We'll see.
Thanks. Yeah, thanks, Daryl. So now we are open for any kind of questions last minute about any topics or any concepts that you may be iffy about, or anything that you would like to clarify. So please shoot questions if you are online, or if you are not. And if you cannot get online, then you can just Chow can collect those and read it out here, and then we can answer those.
Okay. Hey, Ashwa? Vanish. Sorry. Can you explain your questions here?
Okay. I think the first question which I have is about the type of these long questions. So do we need to memorize some of these long questions, or the understanding of concepts should be sufficient to answer those long ones?
No, you don't need to particularly memorize it. You should, if you know the concepts, you should be able to apply those, and you should definitely know the concepts. You should know the definitions. You should know some of the algorithms, how they work in terms of. So what I had recommended was to take some examples, especially for the papers, which are different than given in the papers, and walk through those algorithms. So you should know those algorithms, how they work, what they're trying to achieve, and you should definitely know the abstractions or the representation, such as, for example, interference graphs is one abstraction that we have. And so you should know how the things are represented and how the algorithm uses it, and know the concepts and underlying principles. So that will allow you to. So you should know, for example, concept of what exactly is liveness and how those sets are computed, what exactly is the rationale behind it, and the interference graph, for example, that is constructed, how the coloring takes place. These kinds of clear concepts and algorithms you should know, but you don't have to memorize beyond this point.
Okay, thank you. I think I had just one kind of doubt. What is network processors? Since if the two operands are coming from the same memory bank, it's an invalid instruction, right? So if we have something like A plus B plus C, so does the compiler needs to change it internally into such that it is split into two different instructions with operands coming from different banks? How does it work?
Right. So let us start with the architecture restrictions here and why they are in place. So first of all, the network processors are clocked at a very high frequency of gigahertz, not just couple of gigahertz, but maybe 5 gigahertz and so on many times, which is unusually very high frequency. The reason is this, that of course they had to process information at gigabit Ethernet, and they had to interface with these networks which are operating at very high line speeds. So in order that we keep the clocks that fast, the operations that are supposed to happen during the execution of instructions are parallelized. In other words, if you have two registers which are being added, or some XORed and things like that, they are coming from two different banks because the buses are separate. So what it means is there is a restriction in terms of the two operands being in two different memory banks in order to be processed for very high execution speed. So this is a restriction imposed by the architecture, which is very unusual, that it has a banked memory architecture, and which if the instruction has two operands, then they must come from two different banks. So in order to enforce this, the compiler has to undertake the assignment of the values to the banks. So if you have A plus B, for example, A and B have to be in two different banks. And what happens in this particular process is the paper that we discussed in our class says that if you have A plus B, then A will go to X bank, B will go to second bank. And then if you have C, which is being added, so the result of A plus B will be held in one of the banks. And if C is already allocated to, let's say, bank 2, then A plus B's result will be kept in a temporary, which will be, or a temporary register, which will be in bank 1. So the compiler attempts to make sure that this restriction is obeyed. If it is not obeyed, then it will have to make a copy, move a value from one bank to the other, and then execute that instruction. So it will cost additional amount of operations, and these operations are not, of course, desired, because they will slow down execution. So this is the problem which is being attempted. In this particular problem, what really happens is if you have a cycle that A plus A is being added to B, B is being added to C, and C is again being added to A, as shown in the paper, then this creates some kind of cycles, and you have to break these cycles by doing some transformations, and those techniques are the ones which are shown in the paper. So the restriction of those two being in two different banks is critical, because otherwise it's not a legal instruction for these processors. They will not execute, or they will run into some runtime exception. They have to be in two different banks, because the way the architecture is designed is they're fetched in parallel.
Okay, thanks. One more question that is coming to my mind is, in all this course, we had about 4 different parts, and part 1 was to some architectures of different embedded processors. Then we moved on to compilers, and then we saw some other papers related to different kinds of embedded. So means all the things are equally weighted, right? Means from understanding point of view.
Yes. So roughly, I would say that part 1, dealt with the processor architectures, and we covered. If you look at the pacing schedule, we covered part 1 in first few weeks of classes, so it might be a while since we have done it, and so please go back and also review it, review the homeworks, review the reading material associated with it. So all the parts will be equally weighted, that is correct, and including the papers, the textbook material from that we used in part 2, and also the textbook material in part 1. So please review. They are all interconnected, and the papers build on the concepts of part 1, and also something that we saw early in the part 2, which is about the fundamentals of register allocation, liveness, analysis of control flow graphs. So please review all the material. The lectures should be good to illustrate things, but do read the details from the books as well, and from the papers. And your best bet may be to recreate some examples, work them out, and also go over your homeworks and so on.
Thank you.
Any more questions here?
Not from me as now.
Okay. So there is a question from Jason. I think he is more worried about how many algorithms will be tested, should be remembered for the test.
So most of the algorithms start with the second part, and each if you go through this list, we had in each paper we have at most one or two. Some of them might have two, but there are some examples associated. So I would say that the concepts such as what exactly is the storage optimization problem or MWPC, and then what is the parallelization of load stores, how that is affected by the placement of operands. So the concepts are more important as, and then the algorithms are sort of trying to solve those using certain abstractions. So if you understand the concept and the abstraction, you should be good. The algorithm should come naturally after that. Now, certain things such as what is liveness, if you really understood the live intervals and how those are found, webs, all these issues, I think the algorithms should immediately follow. So I would focus on understanding of the concepts and the representations and how they are being used, and that's how I would understand and the algorithms. You perhaps don't have to as such memorize it, as long as you know that yeah, this is how it really worked on this particular data structure, which is the abstraction that we used. You should be in a good shape. For example, in this odd cycles, in terms of breaking the odd cycles, you should know the concept of bipartite graph and how the transformation is in terms of breaking that odd cycle. So again, it's more of a concept, and if you understand with the help of examples, then you should be in good shape. Per se, there is pseudocode you don't have to memorize, because we are not going to ask you to reproduce the pseudocode in the exam.
Okay, so during the exam, do they need to draw the tables or graphs because they're using the keyboard and the mouse?
Right, so we'll give a way to represent a graph. For example, if you have to show MWPC, then you should show this in a particular way. And you don't have to draw it as an image, but just you can start listing the node, for example, node pairs to represent an edge, a directed edge, if there's a directed edge in the solution or in the question asked. And then you should just list all such things in a particular order. That's what we'll ask you to convert your graph representation, for example, into a linear textual representation. So, because there is no provision in the Proctor tract for drawing a table or an image or a graph, so we'll give you detailed instructions of how to write this in a textual form.
Okay, and for the final grades, is there a hard cutoffs?
No, so the final grades, typically the way we do it is we have given you weightages for different topics, different parts of the class, such as projects, final exam, homeworks, and so on. We will weigh your raw scores with the respective weightages, and we will come up with a final weighted score for each one of you using those weightages. After that, we will curve it based on the ranges and detect the gaps, and then we'll use those cutoffs to give you grades. So there are no hard cutoffs. This is a graduate class, and the relative grade is what will be given. So that is the way we are planning to do it.
Okay. Okay, that is all questions from the Piazza.
Okay, good. Okay, so what we'll do is let's see if some other students are able to join. Thank you, Avnish, for joining and asking questions. Let's see if anybody else is able to also join and ask any questions online or send it to you. And I will mute myself and come back again after a few minutes.
again join back to ask actually the latest directions where this embedded research is going. So, Professor, if you have some of your ongoing projects, what are they, and what is the, I should say, the latest things going on here?
Hello?
Hello?
Yes, can you repeat the questions? I didn't hear it.
Yeah, what I asked is the current directions in the embedded systems research. What are the latest projects maybe going on, and what are some interesting which are going on in research in this field?
Oh, that is a big question. I need to wait in sandwich for your answers.
Yeah, I'll wait for Professor's answer.
Sorry, I was away for a few minutes in between. Were there any questions or any other comments or any such things?
First, I just was kind of thinking, what are the latest research things going on in this area of embedded systems?
Oh,
If you
okay.
have
Sorry, I missed your question. Yeah, that's a good point. So the embedded system started out mainly as they have been there for a while. First of all, initially they were only embedded controllers, which were mostly in aerospace, which were not very interesting because they were very small and they were programmable, but they did not offer any exciting architectures or any kind of things. And later on, with multimedia and printers, especially, became the big consumers of embedded. And the book that you guys read, which is written by Josh Fisher, he was a pioneer in that area. He was at HP Labs. As you know, HP is the leader in printer technology even now, imaging and printers. Xerox was another one, Xerox Palo Alto, copiers and all. Those were other kinds of embedded processors. But the big boost which happened was in terms of the phones, cell phones, in right around the new millennium, or slightly before that, late 1990s. And DSPs became the dominant embedded processors. From there, that evolution continues, as you know, mostly in all kinds of smartphone technologies, um, iPhones and Android, and all kinds of functionality is coming on the phones, which is typically only in desktops. So they become the processors. If you keep looking at the ARM processor lines, which is actually the dominant processor in all these phones, 95% of the processors that are used in smartphones and others are from ARM. You can see that they have become multi-core. So the latest research that is going on is in terms of not single core but multi-core embedded processors, and they tend to have peculiarities. Some of them we have tackled through network processors, which are also extremely high throughput, parallel type of processors, micro engines. So that evolution is continuing. There are all kinds of crazy architectural features such as sharing registers and so on. There was one topic which we did not cover, which is there in your pacing schedule. Those of you who have interest can look at that. That is about the register allocation across different cores or different parallel threads. So that is the state of the art in terms of research, and further research keeps going on in terms of multi-core embedded processors. And latest is this, that the embedded processors are no longer just in terms of standalone systems, but because they offer such huge, especially energy advantages, they are being thought of being used in server farms. So servers are being built on top of embedded processors. Of course, those embedded processors, which are ARM families called KVM, are server class embedded processors, and they will offer a significant amount of computing power at a very low energy budget, at much lower energy budget. Okay, not very low energy budget, but much lower energy budget than regular x86 and other systems. And there are systems which are coming out based on that. So that is fairly complex and totally new use of embedded processors for servers. So that is where things are headed. And I would also claim that GPUs are sort of embedded processors because they are again very peculiar in terms of instructions and the data processing they do and the kind of restrictions they offer. And as you can see, the languages like CUDA tend to reflect the processor architectures being exposed to the programmer or to the compiler. So they are sort of special versions of VLIWs, GPUs. So that's where it's all about the processors becoming more and more energy efficient at high performance. And so these are some of these directions. I refer to some of the conferences in this field to check the state of the art. One of them is called LCTES. The other one is called as CASES, CASES. And the third one is called as EMSOFT, EMSOFT. So many times these are held, some of them are held together as a part of what is called as Embedded Week. So if you search on the internet, something called as ES Week, Embedded Systems Week, you will see a whole bunch of conferences being held together during that week, which expose you to different aspects of embedded systems. So I encourage you to maybe look at their proceedings. For example, EMSoft is a part of ES Week. So I encourage you to take a look at the proceedings, and the field is growing quite a bit here because of, again, the energy efficiencies, and it's getting into mainstream in terms of servers and so on. So as I mentioned, so hope this gives you good pointers for doing something in future.
Yeah, that was useful. Quite useful. Just was wondering. I think would HPC would be a complementary course which you can take or something.
Yeah. So definitely, HPC would be one of them, and the other class could be a compilers class if you really want to get into the total full construction of compilers, being exposed to the it's much more on the software side. So HPC would be more on the architecture and side, but if you want to look at more software side, then that would be compilers class. So both are probably offered in fall. So
One thing which somehow I was under impression while starting this course was I would be able to write some codes maybe or Raspberry Pi or something. So far I have not done anything on other than desktop, I should say. What would be a good starting point for that?
So of course, didn't you do the, of course, Raspberry Pi project, right?
No, that project, yes, that was kind of studying how to
To tune the
optimize,
class. Okay.
how to
Right.
fine tune something on that one. So yes, that one we did, but it was kind of just fine tuning existing code. I was probably I now understand that the coding is not much different as such than what
Not
we.
really, yeah. So, C is the language of choice. C, not even C++. There used to be some really embedded specific languages, but they have slowly disappeared because the code base, it is best to have it in a standard language. As you know, the software engineering principle is that you want to reuse the code, version it, maintain it. So all those specialized languages have disappeared. There are hardly any embedded specialized languages now. So almost all the code for embedded is in C, not even assembly or any of these things, which used to be the case long time back. So
Okay.
it's standard C programming, but most of the time is spent in fine tuning and using the compiler very wisely. So one other thing that you can do is when we do not have access to ARM CC, we use GCC, but ARM CC is one of the top dogs of embedded compilers. So if there is a way you can, you get to use it, different features, flags, and there's a whole development environment which is based on ARM CC. That is something which I encourage you to play with if you can get an access. It is not free. There's a license, of course, and we tried for getting an academic license, but so far we don't have one. So that is one development environment where debuggers, profilers, many performance counters. It's all about tuning. A lot of effort that goes in embedded programming is really tuning.
Okay.
Good questions. I guess we are pretty much at the end of office hours.
Before we leave, I have one question from for course actually. This is about the multi-way and multi-cluster branching. So most of the things which we have seen, except this branching part, we did on a single cluster, a single execution unit kind of thing. So why do we need this multi cluster thing for branching? Is there a particular reason? Is apart from we can just there also, I think the main purpose we were using the other clusters were for computing the branch conditions kind of thing.
Right. So there's not that much use of that. and that's why it is really rarely used in any, particularly in any processors. There was a thought of using it for some kind of a data flow architecture historically, wherein you could fire off based on the ready conditions, and there could be multiple such ready conditions. So that is where that really came from. It is more from the data flow rather than control flow. But you're right, there is not much practical use for that, and mostly it is just for historic purposes. Good. Thanks, everybody. I have to take care of something else as well. Good luck to everybody for their final exams, and hope all of you enjoyed the class, especially the projects. We try to make this course more project heavy rather than we just have one exam, of course, that to test whether we have understood things properly or not and in a comprehensive way. But mostly we have been spending a lot of time during the class on projects and programming. Hopefully all of you had learned from it for whatever purposes you are doing it. Hopefully that purpose is served, and good luck for the final exams. Please do not wait till the last minute to take it on Tuesday. Make sure you finish it before that, because it will cut you off at 9 a.m. even if you are in the middle of it. So please don't wait till the last minute. And good luck, and hope all of you do well. And we will release your grades as per the after we finish grading and so on. And one last thing is I want to thank the TAs who have been the tremendous. They are the drivers of this class, who answer your question, who deal with your difficulties. So without them, this course will not be possible to run. Thanks to Chao and Daryl both for their extraordinary amount of help and in this class. And please do fill up if you have any questions, if you have any suggestions or any comments about the class, what you felt good, as well as for future suggestions. Please do fill up the CIOS. We do look at that, and we continuously incorporate those in the class. So before you are done with the semester, please take a minute and fill up the CIOS. Thank you again, and it was great to talk to all of you during the semester, and good luck for the future. Bye-bye.
Bye.
Thank you all. Bye-bye.
Thanks. Bye.